Welcome back. In this video, we'll explore about capacitance and capacitors. These are essential components in the world of electricity and circuits. Let's start by looking at the basics. Consider two conductors of any shape. One carries a positive charge plus Q and the other an equal but opposite negative charge minus Q. These conductors have a potential difference of V between them. Together they form a system called a capacitor. Through experimentation, we find that potential difference between these two conductors is directly proportional to the charge on them. That means as the charge increases, the potential difference between them also increases. However, the ratio of charge to potential difference remains constant. C is equal to Q by V. This is the ratio known as capacitance. Capacitance is a measure of capacitor's ability to store charge. It's defined as the ratio between the charge on either of the conductors and potential difference between them. In SI system of units, capacitance is measured in farads abbreviated as capital F. 1 farad is defined as the capacitance when a charge of 1 coulomb creates a potential difference of 1 volt. In other words, 1 farad equals 1 coulomb per 1 volt. However, a coulomb is a very large unit of charge, so farads are quite large too. In practice, capacitors are often measured in small units like microfarads, which is 10 power minus 6 farads, or picofarads, which is 10 power minus 12 farads. Now let's look at how capacitance works for spherical conductors. Suppose we have a spherical conductor of radius r. We give it a charge q. The potential V of this sphere is related to its charge and radius. That is, we know that V is equal to 1 by 4 pi epsilon Q by R. And C is equal to Q by V. Substituting this, we get C as Q by 4 pi epsilon naught R, which will be equal to 4 pi epsilon naught R, which can be written as R by 9 into 10 power 9. Using the formula, we find the capacitance of a spherical conductance is directly proportional to its radius. For example, the capacitance of a sphere with the radius of 0.18 meters is 20 picofarads. Capacitors play a key role in universities' power supply system and are crucial components in devices such as radios, televisions, amplifiers, and oscillators. To understand the principle of capacitor, let's consider an insulated metal plate, plate A, and give it a positive charge Q. As we keep adding charge, the potential of the plate increases. However, once the potential reaches its maximum, any additional charge would leak out. Now bring another insulated metal B near plate A. By induction, the negative charge is produced on the nearer surface of B and equal positive charge develop on its farther face. The induced negative charge tends to decrease, whereas induced positive charge tends to increase the potential of A. Now if the plate B is earthed, the induced positive charge on it being free flows to earth, but the negative charge will stay as it is bound to positive charge on A. Due to this induced negative charge on B, the potential of A decreases and its capacitance increases. This shows that capacitance of an insulated conductor can be increased by bringing an uncharged earthed conductor near it. This is the basic principle of how capacitors work. Capacitors are used to store large amount of electrical charge and energy in a small space for short periods of time. They are essential in many devices from power systems to consumer electronics. Let's now consider a parallel plate capacitor, one of the simplest type of capacitor. It consists of two parallel metallic plates, each of area A, separated by a small distance t. An insulating medium like air, paper, mica, glass, etc. separates the plates. The plates are connected to the terminals of the battery. Suppose this plate acquires charge plus Q and this plate acquires charge minus Q when the capacitor is fully charged. The area of this plate B, both the plates be A. These charges set up a uniform electric field between these plates. Here it will be a electric field E. And if Sigma is the surface charge density on either plate. Then the magnitude of electric field between the plates E can be written as sigma by epsilon naught. In sigma is the surface charge density, which is equal to Q by E. So Q by E epsilon naught. This is the electric field. And the potential between the plates is given by, with this the potential between E. So capacitance will be Q by V, which is equal to Q by ED, which can be written as Q by A epsilon naught T. So the capacitance is A epsilon naught by D. Hence, capacitance of a parallel plate capacitor whose plates are separated by distance d have air in between them is given by C naught is equal to A epsilon naught by D, where A is the area of the plates, D is the distance between them, and epsilon naught is the permittivity of free space. This means that to obtain high capacitance, the area of the plate should be large enough and the separation between them should be small. Now, if these plates are separated by a dielectric medium other than the air or vacuum, then the capacitance would become C is equal to A epsilon naught. Instead of the permittivity of free space, we'll be replacing it by epsilon naught. Epsilon can be written as K times epsilon naught by D. This is the capacitance for dielectric medium between the plates, where the epsilon is the permittivity of the medium, K is the dielectric constant of the medium, and epsilon naught is the permittivity of free space. Therefore, we find that the capacitance of the dielectric filled parallel plate capacitor becomes, so now if this few substitute here, we get C is equal to K times C naught. So the capacitance of the dielectric field parallel plate capacitor becomes K times the capacitance with bare or vacuum as dielectric. Now let's explore this concept of relative permittivity, also known as dielectric constant. In vacuum, the force between two charges is given by Coulomb's law. So force between two charges in vacuum can be written as 1 by 4 pi epsilon naught. Two charges be Q and Q2. Distance between them be R. This force depends on the distance between the charges and the permittivity of free space. Suppose this charge Q1 and Q2 are placed in a material medium, the force of interaction between them will be Fm. This is epsilon naught, okay? This will be epsilon. Q1, Q2 by R square. Same distance. So this is in vacuum and this is in material medium. Now from these two expressions, Fv by Fm can be written as 1 by 4 pi epsilon naught Q1 Q2 by R square divided by 1 by 4 pi epsilon naught Q1 Q2 by R square. Oops, sorry. This is epsilon, right? So we get this as epsilon by epsilon naught. The force between them is reduced by the material's permittivity epsilon naught R. This is the dielectric constant of the medium. The dielectric constant of a medium is the ratio of electrostatic force of interaction between two point charges held at a certain distance apart in air or vacuum to the force of interaction between them, held at the same distance apart in the material medium. That is, K is equal to capacitance with dielectric between the plates by capacitance with vacuum between the plates. This can be written as K is equal to Cm by C naught, which gives us Cm is equal to Kc naught. For example, in metals, the dielectric constant is infinite, while in mica or paper, it's around 6 and 3.6 respectively. To summarize, capacitors are essential components in electronic devices and power supply systems, playing a key role in storing energy and regulating voltage. We saw different types of capacitor and also learned about relative permittivity. If you found this video helpful, don't forget to like, share and subscribe. See you in the next video where we'll explore more exciting concepts in electricity and magnetism.